Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CRC in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about breadth first search graph algorithm. So, very first thing is that, so what is a graph actually? So, graph is nothing but a generalization of simple concept of set of dots like links, edges, and arcs. And normally, this graph is going to be represented in the form of vertices and edges, which is going to be have set of vertices that should be denoted by vertex that should be represented as V, or I can able to represent it as V of G, and we can also be represented in the form of edges E, where we can also represent it as E of G. So generalization of a simple concept of dots and links and then edges, arcs, and these are the combination of the graph. So we are able to represent in the form of a vertices and then edges that should be connected. So that should be represented as a graph here. And this one what we call it as an edge, and this one what we call it as a vertex. And vertex set is nothing but the collection of all the vertices, and edge set is nothing but the collection of edges what I'm going to have. So these are the representations of the graph. And graph is going to have just now what I said. So graph is nothing but a set of vertices. So what we call it as a nodes, and set of edges, what we can able to call it as a links. And there are different types of graphs available, like directed graph, undirected graph, and then complete graph like this. Suppose if there is an edge between for every pair of vertices, then I can able to say that should be the complete graph. So if I'm going to have the vertex like this, if I'm going to have an edge from 1 and V2 to V3, and if I'm going to construct this V2, if I'm going to have an edge from V2 and V3 as well, and if I'm going to construct V3 and V1 and V2, so this should be what we call as a complete graph. So for every pair of there should be an edge between every pair of vertices, then I can able to represent that should be called as a complete graph. There are two kinds of graphs available, like undirected graph and directed graph as well. So undirected graph is nothing but a set of two elements what we call it as edges, and it should be also be same as v. That means in the undirected graph I can able to represent v1 v2 on v2 v1 both are same here in case of directed graph, in case of undirected graph. So suppose if I'm going to see the directed graph like this, then v1 and v2 and v2 v1 is not equal. Why? Because I have edge direction only from v1 to v3, and then v1 to v2, sorry, I have an edge direction from v1 v2 and then v2 v1 from going to present in case of directed graph. So v1 v2 is not going to be considered, so v2 v1 is considered. So they should not be equal in case of this undirected graph. And if I'm going to consider this directed graph here, so the other synonym what we called as a digraph, and each the edge set is nothing but set of ordered pairs, and even if you're going to have an edge uv is present, then edge vu also may be absent here. So the directed graphs are going to be drawn with the nodes of vertices and arrows for the edges. So in this case, so this is the directed edge, and I'm going to consider this is the directed and directed, and so that's why this is what we call it as a directed graph. So graph is said to be directed if the edge set is going to have the directions, then I can able to say there should be the directed graph here. And next one, what are the basic terminology you are going to be following graphs here? So adjacency. So what is meant by adjacency here? So the vertex W is adjacent to V if and only if it is an edge set. So if I'm going to consider the edge set here, so the edge set may be 3, 5, 2, -2, 4. Sorry, this and all not edge set. V1, V4, V2, V5, V3, V6, V7, V8. So these are not the edge set here. So vertex V W is said to be adjacent to V if and only if they are going to be coincide with each other. And then weight is nothing but an cost parameter that is going to be associated with each edge, and the path is nothing but the sequence of vertices w1, w2, and so on wn, where there is an edge for each pair of consecutive vertices. And next one is that length of the path. So the length of the path is nothing but the number of edges along the path is nothing but the length of the path, and the length of n vertices is nothing but n minus 1. And the cost of the path is nothing but the sum of the weights of edges along the path is nothing but the cost of the path. So these are the some of the basic terminology you have to be learned in designing the graphs in here. So adjacent means the V1 and V2 are adjacent if there exists an edge between them, and weight is nothing but the cost parameter that is going to be associated with each edge, and the path is nothing but the sequence of vertices w1, w2, and so on wn, where there is an edge for each pair of consecutive vertices. So the length of the path is nothing but the number of edges along the path, and the length of the path of n vertices is nothing but n minus 1. So the cost of path is nothing but the sum of the weights of the edges along the path. And then representing the graph. So here the graphs are going to be represented in the form of matrix here, or adjacency list, what we can able to call. So assume that we are going to have a set of vertices, and adjacency matrix is going to be represent the graph in n by n matrix. Okay, so A of I comma j should be 1 if the edge ij belongs to E, and if it is going to be 0, the edge does not belongs to E. Okay, so this should be an adjacency matrix where we're going to have m number of vertices. So I can able to consider like this. So it should be 1 if there exists an edge between v1 and v2. So that should be 1. Suppose if I'm going to have a graph like this, so v1, v2, and v3. So v1 to v1 is not there, so that's why it should be 0 here. If I'm going to have an edge from v1 to v2, then it should be 1, and v1 to v3 it should be 1. Similarly, v2 to v1 there is an edge, v2 0, and v2 to v3 0. And if I'm going to consider we have only one and one edge, that is v3 to v1, so remaining all 0. So like this, we are going to represent the adjacency matrix of the graph. So let us consider an example like this. So if I'm going to have a graph like this, and we're going to have a set of edges, so whatever the vertices is having, that one I'm going to consider as along the rows and column, then how I'm going to fill this matrix. So in this graph, what I'm going to say, I'm going to have, so 1 to 1, so 1 to 1 is not there, that's why it should be 0. And if I'm going to have 1 to 2, then it should be 1 edge is present, so that's why I'm going to present 1. Similarly, I'm going to have 1 to 3, so that's why it should be 1, and 1 to 4 it should be 0. So similarly, if I'm going to represent 2 to 1, so it should be 0, 2 to 2 0, 2 to 3 1, and 2 to 4 0. And similarly 3, so 3 to 1, 3 to 2, 3 to 3, and 3 to 4. And from 4, 4 to 0, 4 to 1 0, 4 to 2 0, and 4 to 3 1, since I'm going to have only one edge, and remaining it should be 0. So like this, I'm going to represent the adjacency matrix of the given graph. So adjacency list means that, so for every vertex V belongs to V, can able to store a set of vertices that should be adjacent to V. And if I'm what are the adjacency list means, so if I'm going to consider one vertex, so what are the adjacent vertices that are connected to one is that, so two and then three, so this should be the one list. And what are the adjacency of two, that means what are the edges that are connected from two to other vertices, that should be three here. For three there is no vertex that is going to be leaving from the node, so that's why it should be null here. And for four it should be three. So the variation else can also be keep the list of edges that comes into vertex. The next one is that graph searching. So graph searching means, so we can able to explore whether each and every vertex and every edge is going to be present in the graph or not. So how can you able to do that? So by taking a vertex of the root, you can able to search along the vertices and edges of that. So we're going to have different types of searching techniques as well, like DFS and BFS. So BFS is nothing but breadth first search, and this one should be depth first search. So what is this the breadth first search here? So breadth first search is nothing but it is going to explore the vertices of the graph exactly only one time, and then by expanding the frontier of the explored vertices across the breadth of the frontier. So build a tree over the graph such that pick up a source vertex to be root, and then find its children, then their children, and etc. So breadth first search is nothing but exploring the graph by considering the vertices of it. By considering the vertex at a time, so expand the frontier of explore vertices across the breadth of the frontier. And then we can able to build a tree over the graph. So picking a source vertex to root. Okay, so pick up a source vertex to be root here, and then finding the children what are the adjacent to that one. Again, from that, if I'm going to consider, so what are the nodes that are going to be chained of that one. So what I'm going to do that, so again we're going to associate the colors to guide the algorithm. Okay, so for white vertices are not going to be discovered, and then gray vertices are going to be discovered but not fully explored, and then black vertices are going to be discovered and that should be fully explored one. Okay, so I'm going to explain this breadth first search by applying the colors here. So the white vertices are not going to be discovered, and gray vertices are discovered but not fully explored, and black vertices are discovered and explored. So these are the three different colors what I'm going to have in this problem. So if you look at this algorithm, so let us consider the first step should be initialization of vertices, and then we can able to make a queue. So the set of vertices are going to be initialized in that queue, and then until the queue is not empty, how to be remove the top element of the queue. And then so for each vertex that should be adjacent to that, so if v vertex implies color equal to white and v color equal to gray, so what I'm going to do, so I'm going to be mark it as mark 1 and then this problem like this. And similarly, I'm going to enqueue that into the queue. So if it is not that, I can able to mark it as a black. So once this fully vertex is discovered. So this should be the touch vertex of what I'm going to say. So for each vertex, so but only once here, and what should be the every vertex that is going to be appear here in the next of the adjacent list, so that one is should be this one. So what should be the running time of this algorithm? So the running time of this algorithm should be the biggest estimate of vertices plus edges. Okay, so these are the basic algorithm what I'm going to be imposed in that breadth first search. So, so let us consider an example like this. So if I'm going to have a problem like this, so initially I'm going to mark all the vertices should be visited one. So what I'm going to say that is First, I'm going to choose the starting vertex here. So I'm going to take this one as the source. So I have to mark it as 0, and then that one is going to be pushed on the queue, right? So once that one is done, so what is the adjacent vertices that are connected to S here? Only this and this one. So this should be, I'm going to mark it as 1 here, and this one also going to mark it as 1. So these are the two nodes that are going to be adjacent with you. Okay, so I'm going to mark this as the visited one. So I'm going to push this one into the queue. And for S, so R, R and W is booted, right? So then again, what I'm going to construct here is, if I'm going to construct this one, okay. So what are the adjacent vertices? That should be T and then X. So this T and X is going to be pushed onto the Q here, right? So once this one is pushed onto the Q, next I have to find what are the vertices that are connected to R. So that should be V. So V is going to be pushed. So T and already to X and then U. So this should be the next level of vertices in the graph. The next one, uh, if the T is going to be considered, so if the T is going to be considered, so what I'm going to do, so I'm going to take next one, what are the adjacent vertices that are connected to T, so that should be U and then X, right? So this U is going to be pushed onto the Q here. So next one, what I'm going to say that is, so if I'm going to consider U in this case, so what I'm going to do, I'm going to consider what are the adjacent vertices that are connected to U X. So already that one is there. So I'm going to push the Y also marked as the under visiting vertex. So once that one is deleted from the queue, finally I'm going to have U and Y. So these two will be there in the final queue. So this one also removed. So U also visited and then V also visited. Finally it should be empty. So finally the queue is empty. Then there should be the order of that. Okay. So like this, we're going to be find out this breadth first search of the example of the given graph. So initially, what is that? So initially, find out the source vertex, mark it as 0, and push on the find out this R and W here. So what are the what is that are adjacent to W? I have to find it out. So that should be T and then X. So those two will come down the Q. So next I'm going to find out the next one is R. So what are the adjacent vertices? That is R, V. So T, X, V should become. And the next one, what I'm going to take, T is there. So the T, what are the adjacent vertices? That should be U and X. So I'm going to push that U also into the Q. And if I'm going to consider X here, what are the adjacent vertices? That should be Y. So Y is going to be come on to the Q. And finally I'm going to delete V also, and then finally I'm going to have U and V, and this U and V also going to be deleted. Once the queue is empty, there should be the final resultant vertex on the graph. Okay, so further how I'm going to implement this is that by using this algorithm. So here what I'm going to say, here I'm going to have this vertices, initialize the vertex first, and once the vertex is going to be initialized, so we have to be take the source vertex of the graph that should be pushed onto the queue first. So when I'm going to repeat this algorithm is, so when the queue is not empty, so remove the top of the queue, and for each of that, so what I'm going to say, for each V of that have to be considered, I'm going to have three colors, right? So white, green, and then black. So if the white vertex is white, means that should not be visited. Gray means that should be yet to visit, and black means completely visited. So these steps already explained here. So the white vertices are not going to be discovered. That means all the vertices start out white, and the gray vertices are going to be discovered but not fully explored. So that may be adjacent to that white vertices, and black vertices are nothing that should be discovered and fully explored. So this should be the breadth-first search algorithm. So which is nothing but graph traversing technique. And that one is that one I'm going to cover in the next video. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.